Hello, everyone. Now let's talk about operators and observables in quantum mechanics. So operators are a mathematical operation that represents measurements of observable quantities, or things we call observables, in quantum mechanics. These could be things like position and momentum, but could include other types of observable quantities, such as energy. An operator is an operation that acts on a function, and it can change it. It can return a different kind of function. And operators are typically denoted in quantum mechanics, typically represented with a caret symbol above the, say, letter or other mathematical symbol representing the operator, or a tilde uh, over it. So let's consider some hypothetical examples. An operator capital A, notice the hat on it, the tilde, or sorry, the caret, and that operator is a differentiation operator. Okay, we don't know necessarily yet what that represents physically, but it's a mathematical operation. And we have some function, could be a wave function, could be some other kind of function, that's x squared. When we act our operator A on our function f, then essentially we are differentiating whatever function it is that is to the right of the operator. Operators can act in some cases to the left, but we're not going to typically do that this semester. So we can usually assume the operator acts to the right on some function. So using curly braces to represent the operator acting on sort of whatever's inside the curly braces. And so we're differentiating x squared, and the result is 2x. Okay, so somehow this represents a measurement of some physical quantity, some hypothetical physical quantity associated with the operator A. And we can consider another function, or wave function, e to the ax, a simple exponential, where e here is Euler's number. It's the 2.72 something irrational number. So that's the base e of, say, the natural log. If we act our, and exponential functions will come up quite a bit this semester. So this is a good example. So if we act our operator on our function f, we get back a e to the ax. That's the derivative, the first derivative of e to the ax, which you can know from a table of derivatives or by applying the chain rule. So that was just a couple of quick examples. Now let's move on. That's one kind of operator, a differential operator. Operators can include a fairly wide variety of mathematical operations. Such as So fairly simple ones like multiplying by a constant. Multiplying by a function. Say a function of x or a function of x, y, and z. Differentiation, as in our example above. But not just the first derivative, it can also have second derivatives. And in each case, you would think of it as acting on whatever function happens to be to the right of our operator. And finally, we can have sort of composite operators, which are sums and products of other operators. Or even in some cases, functions of operators. For instance, there's the time propagation operator, which has an exponential, and it has the operator h inside the exponential. However, there are some restrictions on operators in that we say, or rather, we can classify operators, and then once we've classified them, we can impose a restriction, or we can talk about certain restrictions that may apply regarding this classification. So a linear operator obeys this relationship such that if we act an operator on the sum of two functions, that's the same as the sum of that operator acting on each function separately. And it turns out that all of the quantum mechanical operators that we're interested in are linear. It turns out that all quantum mechanical operators are linear. And an example of a nonlinear operator would be something like square root. Square root of f1 plus f2 is not equal to the square root of f1 plus the square root of f2. Now that may be true in some isolated cases, but it's not generally true. So we're not going to see a square root operator, for instance, as one kind of operator. Here's one kind of operator that we've seen already. And that's the Hamiltonian operator. And this is a very important operator in quantum mechanics. It's given by H, again with the caret. And H is equal to minus H bar squared over 2m del squared plus V. And we can see this obeys the rules that we've set up for how you might be able to construct an operator. All of the pieces of it are either derivatives or functions or constants. And this is a sort of composite operator that has second derivative and multiplied by some constants, h bar squared over 2m minus h bar squared over 2m, plus v, which we're going to assume is a function. It's our potential energy function that we saw previously. You do remember this from 1 or 2 videos back, right? Okay, if not, be sure and review videos and see if you can recall the key concepts. All right, so then we can rewrite our Schrodinger equation in this operator form. Or sort of a condensed operator form. H psi equals E psi. And the Hamiltonian operator is essentially distributed, right? Distributes these two terms, the del squared term and the potential energy term, over psi. So, yeah, so we have to use that distributive property to evaluate it. Now, one thing that I'd like to mention quickly, why is this called a Hamiltonian operator? There's a classical formulation of Newton's equations, essentially, called Hamilton's equations. And in Hamilton's theory, it's based on conservation of energy. And so in classical Hamiltonian theory, H is kinetic energy plus potential energy and that of course gives the total energy of the system. So again, quantum mechanics is borrowing from classical mechanics. Not classical mechanics that we may have learned, but nevertheless, that's where that comes from. Now let's move on to the concept of a correspondence principle. There are different versions of the correspondence principle. In both cases, they relate to conversion rules for converting from classical observables, in other words, observables that we know about in conventional physics, and we convert to quantum mechanical operators. So there's a set of conversion rules. Sometimes those conversion rules are referred to using the correspondence principle, by calling them the correspondence principle. And the basic idea is that for every classical observable, there is a quantum mechanical counterpart represented by an operator. Okay, for all or for every classical observable, there is a quantum mechanical counterpart. And there are some fairly straightforward conversion rules. First of all, we have our position operators, x with a caret, y with a caret, or z and z with a caret. And in any expression for a classical observable, you would replace any instance of position with one of these, with the appropriate position operators. And similarly, but it turns out that these operators have a straightforward mathematical representation. The x operator is represented by multiplication by x. And we'll see how that works in a little while. And the momentum operators, according to the postulates of quantum mechanics, which are well justified, but nevertheless we often treat them as postulates. The momentum operators along the various axes are denoted using P with a caret. And in terms of the function, the actual mathematical operation associated with those operators, momentum along the x-axis is given by minus I h bar d dx. And similarly, the momentum along the y-axis, its operator is represented by the mathematical operations minus I h bar d dy, where again h bar is h Planck's constant divided by 2 pi. And Planck's constant is 6.6 626 times 10 to the minus 34 joule seconds. And finally, the third principle of this, the third leg of this correspondence principle is that all of our other operators or observables are built from these. For instance, let's consider the classical quantity, the classical observable angular momentum, right? We might want to have, we might have some system that has some rotation in it or some motion about some central point, and there's a corresponding angular momentum, and angular momentum is a vector quantity, and it's given by R cross P, where that X there is not multiplication by X, it's a cross product. A vector cross product. And this is often represented using a determinant where we put unit vectors along the first row, we put the position x, y, and z along the second row, and we put the momentum in the third row, and so this cross product ends up giving us a vector that is perpendicular to the plane of rotation. So if you have rotation in the xy plane, then you have angular momentum axis pointing along the plus or minus z axis. So if you have, say, like a bicycle wheel spinning in the xy plane, then there's going to be the angular momentum you can think of as sort of sticking out of the hub of the wheel, perpendicular to the wheel. And it follows, of course, the familiar right-hand rule. Okay, so that's just a little review of another little piece of classical mechanics. Now let's try to, now if we want to look at various components of that, we can look at this by inspection. As I said previously, if you have motion in just the xy plane, rotational motion in the xy plane, then you're going to have angular momentum along the z-axis, and so we can break this down into various components. Lz, for instance, is xpy minus ypx, right? So you'd have this k here representing the unit vector along the z-axis, and you have xpy and ypx, right, in our determinant. So similarly, we can, so that's the classical angular momentum along the z-axis, the angular momentum component along the z-axis. If the quantum mechanical counterpart then is going to be Lz is equal to xpy minus y px, or minus I h bar x d dy plus I h bar y d dx. Where I took the liberty of moving the constants, the I and the h bar, out front. And there are other operators for things like, say, mu, dipole moment operator, or the time propagation operator that I talked about. There's also operators for rotating a system. So operators can represent measurements, but they can also represent things that are done to the system. So some external influence on the system that's either, say, rotating the system, translating the system, or moving it forward in time. And I think that's a good place to stop. The next video will be about expectation values of operators. So we've said that operators represent measurements, but there's another piece that we need to set up in order to actually represent a complete measurement of a system.